Hello everyone! Thanks for joining our third part of the video, What Algorithms? In the first part, we started discussing algorithms and different goals for different people when developing algorithms. As well as we started thinking what considered to be effective algorithm, with focus on its faster running time. In the second part, we discussed how roughly we can estimate algorithm runtime by using order of growth concept, also named Big O. Let's move to the next topic, decomposing, reduction. I want to talk about important technique named reduction to use when you design algorithms. I can see it as a possibility to split, divide overall task into subtasks whenever possible. Once it's done, you can try to find the best algorithms to solve each subtask. The best, for example, in terms of Big O notation, how efficiently fast each subtask can be executed. Or maybe you are dividing tasks into subtasks, already knowing how effectively to solve each subtask. If each part can be solved the most efficient way, then overall task will be solved the most efficient way as well. The only trick part is to find patterns, similarities, to see how to divide overall task into subtasks, which might not be often so easy. Let's look into a few examples of a problem reduction. It's very often when one of the subtasks is about sorting items. If you know sorting algorithm with the best Big O and log n, and other subparts of whole problem can be done also efficiently, it makes sense to use reduction to divide into subtasks to solve each of them the most efficient way. Some problems are more or less obvious to discover that sorting algorithm to be used. Let's mention them. Example number 1. When you use your mobile phone's contact list, imagine that it's not sorted by names. To find person, in the worst case scenario, when contact you need to find is at the very end. Then you need to list through all names from the beginning. But when it's sorted, you can jump to the blocks of names in the list started from the letter you need. Example number 2. When you need to find 3 smallest numbers in a set, instead of 3 times searching for smallest number, it probably makes sense to sort set of numbers in ascending order. Who knows, your algorithm periodically may check first several smallest numbers in a set. Once you sorted items in a set, you can reuse it several times later. Example number 3. Geometrical task now. When you have several points on our two-dimensional plot, the task is to connect only external points which will compose convex hull. If we by mistake will add drawn point, we may end up to have concave hull instead of convex. In other words, algorithm provides a wrong result. One of the algorithms behind constructing proper convex hull is to select one point, which definitely should be part of outline of our convex hull, for example, the lowest value on y-axis. And then we need to imaginary connect other points to selected one. Streamline all lines counterclockwise. Then the idea is to start connecting first point with the second, second with the third, and so on. A line must be kept on the border of our convex hull only in case we always turning kind of left, if compared with the direction of the previous line. Geometrically internal angle between lines should be less than 180 degrees. If we turn in right, that means that previous point or even several points reside inside the convex hull and needs to be excluded from convex hull border. Otherwise, we may have concave hull instead. Excluding can be done by connecting new point with the closest previous one, which will end up turning lines left. Principle of constructing geometric figure is simple to visualize. But you may ask, what kind of sorting needs to be done here, since we're discussing topic about reduction, separating tasks into subtasks. If to think geometrically, when you need to streamline all imaginary lines counterclockwise, you actually sorting lines in terms of increasing polar angles. Isn't it elegant? Definitely sorting. Let's wrap up. We can try to split, divide overall task into subtasks whenever possible. Once it's done, we can try to find the best algorithms to solve each subtask. Important definition to remember, which is related to splitting task. They say initial problem number 1 is reduced to problem number 2 if you can use an algorithm that solves problem number 2 to help solving initial problem number 1. In our recent examples with several smallest items or convex hull, We were helping to solve initial problem by using sorting algorithms. And of course, we need to know which sorting algorithm to be the most efficient. Moving to the next topic. Since sorting algorithms are heavily used, let's start with some well-known among them. Look to a few examples and check how we understand order of growth. We will look into 3 examples, with their names respectively: insertion sort, merge sort, and quicksort. First of all, I want to mention that our goal is not to show how to implement algorithms on any programming language. Remember, an algorithm can be specified different ways, for example in English or as a computer program. The only important requirement is that specification should provide a precise description of the procedure to be followed. We will talk based on general abstractions to understand the idea and how potentially to implement algorithm. First of all, what is the task for a sorting algorithm? It takes input data in form of sequence of n elements, for example numbers, characters, or any other elements, which can be compared to tell which one is larger or smaller. Output data of an algorithm should be another sequence with the same n elements based on reordering of input sequence, such that next element should be not less than previous element, like in our example. For example, numbers to be in ascending order, characters or even strings in alphabetical order, sort files in a directory by name, and so on. Before we proceed with algorithms examples, let me bring one term to the plate. In-place algorithm is an algorithm which produces output in the same memory or place that contains input data. So no extra data structure of input data size is required, but just small memory for temporarily holding particular element. In real life, we can think of analogical examples. You have cabinet with several shelves with unsorted documents considered as input data. When sorting, you take each document from this cabinet and put it in order into second different cabinet with the same amount of shelves. Such separate cabinet will eventually contain output data. That means twice more space is needed for storing data. And second example is, you compare 2 documents in the same cabinet for the purpose of sorting. Algorithm may just move documents between shelves of the same and the only cabinet. Or sometimes algorithm needs to swap documents, still in the same cabinet, but may not have extra space on any shelf. So it may temporarily take one of the documents out from the cabinet for a while, put second document on its place, and freed up space from the second document needs to be filled by the first document. Such algorithm may have lots of replacements, but all of them will be within the same cabinet, with potential storing single items, documents, temporarily outside. No need to have second cabinet of the same size for such algorithm. Therefore, among 2 algorithms, only second one requires just the only one cabinet for the input and output data, and such algorithm is considered as in-place algorithm. Why we mentioned in-place algorithms? Often algorithms implemented as in-place algorithms for memory economy, but in our analogical examples it might be easier to understand idea without keeping in-place approach in mind. We may also start with one approach and show how to implement with another one. By the way, some algorithms become very complex in case of in-place implementation. For simplicity, it's better to avoid in-place implementation sometimes. Going next. If you need to sort a set of numbers, what would be the easiest way to make working solution for sorting in ascending order? The easiest for me is a brute force type algorithm. To find smallest item among all, put it on the first place. For in-place approach, we can swap smallest number with the first item, if the first is not already the smallest one. For example, in the set of 7, 3, 6, and 10, item 3 goes to the first place. First element 3 considered to be part of final sorted sequence. Then I would look to the smallest item among not yet sorted numbers, 7, 3, and 10, which is 6, and put it on the next second place in final sorted sequence. After 2 steps, we have 2 first elements which are considered as sorted. On the third step, we need to find smallest item and put it on the third place. Item 7 looks like should stay on its place, since it's the smallest one. There is no need to do anything with the last item. It should be already not smaller than any other already sorted elements. Often algorithms were given names. This one actually also has name selection sort. But like other brute force solutions, it gives obvious intuitively working solution. You definitely take into consideration all input data, but it's not optimal from runtime perspective. On each step, you check all unsorted elements to find smallest element among them. You are not skipping any element regardless of input data set, which might be already partially or even fully sorted. So your worst case for order of growth proportion will be almost the same as average or even the best case. Algorithm will be checking all unsorted items over and over. Therefore, let's look into a couple other not brute force solutions and see how optimal they are. Let's continue with insertion sort algorithm. Its main idea is similar to sorting playing cards. Player has pile of cards on the table, faced down. Pile of cards contains input data. Empty left hand at the beginning will contain output data. Then player takes one card at a time from the top of a pile and insert it into correct position in the left hand. To find the correct position for a card, we compare it with each of the cards already in the left hand, for example from right to left. Exception is only for the first card. It comes to the leftmost position because there are no cards to compare with. Very important to notice. At all times, the cards in the left hand are sorted. That statement is applicable to the point when algorithm is completed. So algorithm is always correct, provides proper results, sorted sequence, regardless of input data and its size. Let's look to the example. Let's say you have pile of 6 cards, 5, 7, 4, 2, 5, 3 on a table. Face down so player, who is about to sort them, cannot see them. I'll keep them shown for you, like having transparent table made of glass with camera on a floor facing up. Both player and our algorithm will know each card at a time of taking card from the top of a pile, similar to a computer which is given instructions to work with particular item at a time. First card 5 comes to the leftmost position in hand, and it's self-sorted. Then we take next card 7, compare it with the rightmost card in hand, which is 5, and put it on the right, because 7 is not less than 5. Then we take next card 4, compare with 7, it's less than 7, therefore we continue to compare with the next to the left item 5, and conclude 4 is less than 5. No other items on the left, so 4 should go to the leftmost place. We need to move cards 5 and 7 one position to the right. Please check that cards 4, 5 and 7 in hand are sorted. They are sorted after each step and will be sorted at the very end once all cards from pile are taken care of. Next step. Same thing with the next card 2 in pile, comparing with 7, 5, 4, concluding to put on the leftmost spot, moving other cards in hand one space to the right. Next card 5 to compare with 7, then compare with 5. Since it's not less, and not less includes equal, then new card 5 goes between 7 and already sorted card 5 in hand. Therefore we move only card 7 one space to the right, once new card 5 takes its place. And the last card 3 in the pile, comparing it with 7, 5, 5, 4 and 2, concluding that it should be between cards 4 and 2, moving to the right several cards, 4, 5, 5 and 7. Eventually we have all cards taken from a pile and sorted in hand. Insertion sort is done by one card insert into correct position in the left hand on each step. By the way, pile and hand are two separate allocated spaces, so our example was not about in-place implementation. But technically insertion sort is easy to implement as in-place algorithm. Note, when you implement in-place algorithm to run on a computer, you may need to temporarily store items outside of initial input data allocated memory block. Imagine you have 2 shelves for documents. You have space only for one pack of documents on each shelf. Since you have space only for one document pack, if you put another document on a shelf, existing document will be thrown away. No space for both documents on a shelf. Computer also rewrites old value with a new one in the same memory spot. As a solution, you can temporarily put one document outside of a cabinet with shelves considered as storage for your initial data and at the same time for output data of in-place algorithm. so you temporarily put document, let's say, on a table. Then freed up space can be used for placing another document. And once document moved from one shelf to another, space is ready to put document temporarily stored on a table back to cabinet with shelves. At the end, you swapped documents within the same cabinet without losing, overwriting any document. But we need to temporarily use external space for a single item for a while though. Returning back to in-place insertion sort algorithm. For simplicity, you still can imagine pile and hand, but cards shuffling will be within the same space. 5, 7, 4, 2, 5, 3. Next step, 5, 7, 4, 2, 5, 3. Next step, 4, 5, 7, 2, 5, 3. Next, 2, 4, 5, 7, 5, 3. Next, 2, 4, 5, 5, 7, 3. And finally, 2, 3, 4, 5, 5, 7. When computer runs algorithm, you need to remember that it needs to take care about one item at a time. When you need to move several cards to the right, it will move one by one. So when you place card 4, two cards 5, 7 are moved separately, similar to documents in the shelves, freeing up space for each next step. Card 4 stores outside at first step. It's space to be used to place card 7. Freed up space from card 7 can be used by card 5. And then card's 5 space is used to put card 4, temporarily stored outside of our input-output data space. Similar process is used later when you move other cards. How many steps such algorithm can have in the worst case? Let's remember our order of growth topic. It will be oversimplifying sometimes to focus just on significant items. First of all, algorithm will have n steps to compare each element with others on the left, from the beginning of our set, where n is the size of input data, 6 cards in our example. Technically we have n-1 step, because for the first item algorithm doesn't do anything. But when n is large, n-1 is so very close to n. For simplicity, let's have n steps. On each step, you may need to compare a value with up to n items on the left, n-1 to be precise. And in the worst case, after comparing, you may need to move up to n items to the right, n-1 to be precise. Both comparing and moving operations can be up to n plus n to multiply n on each of the n steps. Which means that our order of growth, our proportion between input data size n and runtime is quadratic for insertion sort. For our proportions, we ignore leading coefficient. And moreover, I oversimplified and didn't make precise calculations. Actual coefficient will be lower than 2, and anyway to be ignored. Because up to 2 multiply n operations in the worst case can be only at the very end of the algorithms, when you need to compare the rightmost element with the rest of them, and may move up to all of them. At the very beginning of algorithm, number of comparisons and moves will be lower. Whoever wants to have precise formula can dive into arithmetic mean idea. But again, for our rough estimation, we ignore coefficients and emphasize on quadratic order of growth for insertion sort. There are several other correct algorithms for sorting, giving the same proper results, but applying different approaches and therefore working at a different speeds. You can check yourself bubble sort, selection sort, shell sort, certain variety of insertion sort, to practice and see ideas underneath of correct algorithms. My recommendation is to pay your attention to merge sort as the very efficient algorithm. For learning merge sort, you need to know idea of recursion and recursive algorithms though. Let me give a simplified idea in couple of words. When we discussed data types in a separate video, we mentioned a data type is said to be recursive if a value of the data type can contain or refer to another value of the data type. And tree was a bright example of such data type. Any part of a tree, its any branch, can be seen as a smaller subtree. In that video we also mentioned procedure data type. This data type takes some parameters of different types, comprises the set of all operations and returns some value of certain data type. Such procedure can contain instructions for sorting to implement our algorithm. Algorithm considered to be recursive if it contains procedure which calls itself directly or indirectly through different procedure. Such procedure, also can be named function, is called recursive as well. When we call recursive procedure, it looks like an endless loop, isn't it? But the trick is, every next time it generally takes smaller input data size than during previous call. And eventually input data size becomes so small that there is no longer need to call a procedure. That's how we can end the loop. It's like visiting all branches in a tree and coming to a last leaf in a tree. You don't have any small tree branch here. Your branch is technically the last leaf. The idea behind it, solution of a bigger problem, could be found by solving smaller similar problems, analogically to describing recursive data type. For example, a tree from my recent example. Another idea behind it, you can simplify your software code, make it very compact, because regardless of number of recursive procedure calls, you use the same limited number of steps of the same procedure. In other words, huge amount of steps at a time of algorithm execution can be represented in just few lines of code. To me, it's very elegant. So once you digest recursion concept, you're welcome to learn merge-sort recursive algorithm yourself. I will bring just one more and actually last algorithm in this video, Quicksort, which is also a recursive algorithm. Quicksort considered as one of the top 10 algorithms of 20th century in science and engineering. It's widely used in Java, C, Visual C++, Python programming languages, interpreters, in Linux, in Unix, MATLAB, and so on. It's worth to dig into its details to understand such success. Let me list basic steps of Quicksort algorithm first, and then I will clarify a little bit more. These sorting steps are: shuffle input data set, one-time preliminary step. Partition set into up to 2 parts divided by selected element named partitioning element the following way. Select arbitrarily partitioning element. No larger items compared with selected element, if any, to put to the left of the selected element. No smaller items, if any, to put to the right of the selected element. Sort each, if not empty, left and right pieces of set recursively. In other words, you go with the same partitioning described on previous steps for each left and right pieces of dataset, except preliminary shuffling. Let me make few comments for clarifying design intent. Partitioning element is selected arbitrarily, instead of spending time to find arithmetical mean value or any other way. That's huge runtime saver on each step. Once partitioning element is selected, the size of the rest of input dataset will be one item smaller. In most cases there will be 2 subsets, on the left and right sides, so size of each subset therefore will be even smaller. Sometimes it could be even 1 subset instead of 2, if arbitrarily selected partitioning element is the leftmost or rightmost. So we have smaller and smaller input set sizes on each further step of recursion, until reaching just 1 element on each subset. Remember, algorithm does not do anything at all for a subset of size 1. This is a terminating point of all recursive loops. We need to remember, after each recursive loop, partitioning element stays on its place, considered keeping its place in final sorted set. On the left side we have no larger values, on the right side we have no smaller values, compared to partitioning element. But on each side they are not guaranteed to be sorted until we move deeper to subsets of size 1. That's why we need recursion to reach subsets of size 1. Let's have an analogical example with cards. This will be our initial set of cards: 6, 8, 9, 2, 7, 5, 9, 10. On the first step we need to shuffle it, so it will be random changing places for all cards. Let's say we have this set of cards after shuffling: 9, 10, 2, 6, 5, 9, 8, 7. Then we will have first loop of our recursion, partitioning process. We can implement it the following way. Arbitrarily take the very first leftmost element to be partitioning element. Within the first loop for our set, it's card 9. If we found no larger values, they will be placed on the left side of this element. Let's see how. Introduce pointer low to the second element and increment it, if needed, till finding no smaller value compared to partitioning element. In our case, second element 10 is no smaller than 9, found right away. Introduce pointer high to the last rightmost element and decrement it if needed till finding no larger value. In our case, 7 on the rightmost place is no larger, also found right away. If both no larger and no smaller values were found, they need to be swapped. So we are swapping items 10 and 7. Repeat previous two steps until pointers are crossed, which means no other elements left unattended within particular recursive loop. Numbers 2, 6, 5 are smaller than partitioning element 9, so in our case, low pointer will be incremented until reaching item 9, which is no smaller than partitioning element 9. High pointer is to be decremented just one time, because item 8 is no larger than partitioning element 9. Swapping 9 and 8. If we increment low pointer and decrement high pointer further, they will be crossed. That means we need to stop with current recursive loop. We checked all elements, and in particular case we found two pairs of elements which were swapped. As a result of first loop, elements 7, 2, 6, 5, 8 on the left are no larger than partitioning element, and elements 9, 10 are no smaller than partitioning element. So we have two subsets for further recursive sorting. The last step, once pointers are crossed, we just need to put partitioning element between subsets. High pointer after last decrement points to the rightmost element of the left subset 8. Since we don't care how elements are sorted within each subset, we just swap partitioning element with 8. Current set exactly following initial design intent of Quicksort recursive step. Select arbitrarily partitioning element, in our case 9, no larger items compared with selected element if any to put to the left of selected element, no smaller items if any to put to the right of the selected element. Then we recursively sort each subset 8, 7, 2, 6, 5 and separately 9, 10. FYI, in software developing, they call exceptional extreme case as an edge case, when standard homogeneous approach may not be applicable. In Quicksort, there might be such edge cases, a chance that even one first value pair, both no larger and no smaller candidates to be swapped, could not be found during our recursive loop. That means partitioning element is either the largest or the smallest. If it's the smallest, partitioning element stays on the same leftmost place, left subset considered as empty. If it's the largest, it goes to the very end, right subset considered as empty. In our example, such edge cases are happening. Sorting recursively subset on the left side, 8, 7, 2, 6, 5, applying the same steps. Partitioning element is 8, the leftmost. Introduce pointer low to the second element and increment it if needed till finding no smaller value compared to partitioning element. As you can see, we cannot find any elements not smaller than 8. In this case, partitioning element to be swapped with the rightmost element, as it's the largest one. We don't have second subset on the right in this case, just one subset on the left, 5, 7, 2, 6. Applying the same steps. Partitioning element is 5, the leftmost. Introduce pointer low to the second element and increment it if needed till finding no smaller value compared to partitioning element. 7 is not smaller. Introduce pointer high to the last rightmost element and decrement it if needed till finding no larger value. In our case, 2 is not larger element. If both no larger and no smaller values were found, they need to be swapped. So we are swapping items 7 and 2. If we increment low pointer and decrement high pointer further, they will be crossed. Stop current recursive loop. Put partitioning element between subsets. Swap partitioning element 5 with element 2 pointed by high pointer after decremented on previous step. So we have subset on the left with just one element, 2. Such subsets are not subject for further sorting. Recursion will be terminated for this subset. Sorting recursively subset on the right side, 7, 6, applying the same steps. Partitioning element is 7, the leftmost. Introduce pointer law to the second element and increment it if needed till finding no smaller value compared to partitioning element. We cannot find such, so we have edge case when partitioning element is the largest and needs to be put on the rightmost place. 6, 7 is our result. No subset on the right. Subset on the left contains just one element, a recursion to be terminated. We finished all recursions for the left subset after the first loop, but we have right subset 9, 10 to be taken care of, applying the same steps. Partitioning element is 9, the leftmost. Introduce pointer law to the second element and increment it if needed till finding no smaller value compared to partitioning element. 10 is the right candidate. Introduce pointer high to the last rightmost element and decrement it if needed till finding no larger value. No such value found. Pointer is crossed. That means our partitioning element is the smallest and needs to stay in its place. Result contains no subset on the left, partitioning element 9 and subset with one element 10 on the right. Recursion for subset of size 1 is to be terminated. So we reached all termination points for our initial set. Final result is our sorted set 2, 5, 6, 7, 8, 9, 9, 10. Hope you understood how recursion works better, clarified how Quicksort works in general. Few extra comments. Preliminary step shuffling allows us to arbitrarily choose partitioning element and minimize edge cases, which means to have two subsets more often to the left and right of partitioning element, which makes algorithm more efficient from runtime perspective. It's better to implement Quicksort algorithm as in place. It's one of its biggest advantages. For order of growth, for most average input data, Quicksort turned out to be the fastest in practice among other algorithms. Remember table of runtime comparison between insertion sort and Quicksort we showed before. Let me give you known pre-calculated estimation. Average case has linearithmic n log n order of growth. Technically speaking, in the worst case we have quadratic n squared order of growth. But initial shuffling increases chances to move away from the worst case to an average scenario. We almost finished current video answering question what is algorithm in software developing. We covered following topics and terms. Algorithms are methods for solving problems in a broad sense. In particular, to search for some meaningful information subset out of a large preliminary collected initial data. We mentioned different approaches when developing algorithms. Students may use algorithms as side effect just to practice. All developers and interview candidates need to have always working algorithm. An algorithm is said to be correct if, for every input instance, it provides correct output. We mentioned brute force algorithms, which check all possible input data using exhaustive solution search. Great developers and candidates follow client needs, who is craving for efficient algorithms. Curious minds and this video's listeners want to understand how algorithms work. Then we discussed classification of algorithms' effectiveness with focus on runtime. We started with accurate mathematical models to calculate running time by summing up all cost multiplied by frequency for each operation. Operation cost depends on computer and programming language, system-dependent factors. Operation frequency depends on input data values and size, as well as depends on how well algorithm is optimized, system-independent factors. Optimized algorithms have greater impact on program runtime than your computer, and developers have possibility to make an impact by optimizing algorithms. Then we moved to order of growth topic to classify algorithms, named as BGO, which is not accurate model, rather rough estimate, but still effective instrument. It's based on idea that generally if input data size increases, consequently overall program runtime is growing. Remember, input data size is not known at the time of writing a code. We can actually measure in practice runtime for different input data sizes. Or we can analyze code and predict what will be the runtime based on input data size. Proportions between input data size and runtime is the main focus of order of growth. Therefore, for simplification, some coefficients and less expensive or less often operations are discarded. Common big O classifications discussed: constant, logarithmic, linear, linearithmic, quadratic, cubic, exponential. Generally, constant type is faster than logarithmic is faster than linear, and so on. You need to avoid cubic algorithms. You also need to avoid exponential algorithms as an example of non-polynomial runtime, because they are even intractable. Scientific approach to design algorithms consisting of cyclic multi-step activities allows to find better algorithm by reducing frequency of operations and move from slower to faster in terms of big O classification algorithm. We saw examples of real runtime for two algorithms: insertion sort, quadratic type, and quicksort, linearithmic type, and saw that even supercomputer will spend 1 week sorting billions items using insertion sort, while it will be nearly instant for the same computer to sort the same billion items using quicksort. Your slower home computer will spend 317 years and 20 minutes respectively on the same tasks. Some scientific-grade algorithms were discovered 10, 20, 30, 50 years back, and they are still fastest till nowadays. Next topic was about decomposing, reduction technique. Idea is to split, divide overall task into subtasks when possible. Then you can find the most big O efficient algorithm among existing for each subtask. They say initial problem number 1 is reduced to problem number 2 if you can use an algorithm that solves problem number 2 to help solving initial problem number 1. We saw few examples when sorting was one of the subtasks. 3 smallest numbers, convex hull. You can imagine, would it be better to use insertion sort or quicksort to implement overall algorithm? And finally, we discussed implementations of insertion sort and quicksort algorithms. We discussed what sorting algorithm is. We introduced few terms: in-place algorithm, which uses same memory for output, which is used for input data as well, and recursion, recursive algorithms. Algorithm considered to be recursive if it contains procedure which calls itself directly indirectly. In the very next video, we will discuss why you need to learn topic about algorithms. We will also mention several use cases and typical algorithms used in computer science. Stay tuned, it should be interesting, and see you there!